Now let me introduce an important notation. So I have L, an extension of K, and alpha, an element of L. I call K of alpha the smallest subfield of L containing K and alpha. And I call K of alpha in the square brackets the smallest subring, or a K algebra if you wish, containing K and alpha. Well, let me give you an example. Well, first of all, let me say that K of alpha in the square brackets is generated as a vector space over K by 1 alpha, alpha squared, and so on, alpha to the power n, and so on, by the constants and all the powers of alpha. So let me give you an example. Of course, C is equal to R of I as a field, but it is also equal to R of I as a ring, because any element of C is x plus I, y, where x is a real part and y is the imaginary part. So, of course, this is a vector subspace generated by 1 and I. And this is a general phenomenon. So, proposition 1, the following conditions are equivalent. First, alpha is algebraic over K. Second, that K of alpha as a ring is a finite dimensional vector space over K. And third, K of alpha as a ring is equal to K of alpha is a field. So let me prove this proposition for you. Let me prove that 1 implies 2. If alpha is algebraic, then I can write alpha to the power of d plus a d minus 1 alpha to the power of d minus 1 plus, and so on, plus a1 alpha plus a0 is equal to 0, where ai are elements of K. This is just P of alpha, where P is a minimal polynomial. So, we see that alpha to the power of d is minus a linear combination the sum of ai alpha to the power I, where I is from 0 to d minus 1. So you see that L alpha to the power of d, alpha to the power of d plus 1, and so on, are going to be linear combinations of the lower powers of alpha. This implies, of course, that K of alpha is generated by 1 alpha and so on, alpha to the power of d minus 1 over k. And in particular, it is finite dimensional. Let me prove that 2 implies 3. Well, it is enough to prove that k of alpha is a field. Since, of course, k of alpha in the square brackets is contained, and k of alpha with the round brackets. Well, how do you prove this? It is very simple. Well, let x be an element of k of alpha. I want to show that this is invertible. Consider the multiplication by x. So this is the multiplication by x. This is a homomorphism of vector spaces. This is an injection of vector spaces over K. But we know from linear algebra that if you have an injection of finite dimensional vector spaces of the same dimension, then it is also a surjection. Since K of alpha is finite dimensional, this is a surjection. So there exists a y in K of alpha such that y times x is equal to 1. So x is invertible. X is invertible and K of alpha is a field. Of course, I have forgotten to say that x was supposed to be non-zero in order to have the multiplication by x injective, but I guess everybody has understood. So we were assuming x non-zero from the beginning. Okay, so let me prove that 3 implies 1. So if K of alpha in the square brackets is a field, then alpha is algebraic. This is maybe the easiest part. So if alpha is not algebraic, then there exists no polynomial p such that p of alpha is 0. But what does this mean? This means that a natural homomorphism, let me call it I, from kx to L, which sends P to the P of alpha, is injective. But K of x is not a field. K of x is not a field. And the image of this homomorphism is K of alpha, which is a field. And the image of I is a field, because this was just K of alpha. So this is a contradiction. Definition: L, an extension of K, is called algebraic over K if every element of L is algebraic. Oh, let me give you some properties of those algebraic extensions. Proposition 2. If L is algebraic, over K, any K subalgebra of L is a field. Any K subalgebra of L is a field. Well, proof. Let's take L prime in L, a subalgebra. Fix an alpha in L prime. I have to show that it's invertible. Well, I know it's algebraic. And then I know that K of alpha, which is also a subalgebra of L, is a field. And then I know that alpha is invertible. And since I can do it for any alpha different from 0, it follows from this that L prime is a field. Well, another proposition which will be important is as follows. Let's have K in L in M. If alpha in M is algebraic over K, then it's algebraic over L, and it's minimal polynomial. Over L divides its minimal polynomial over K. Well, this is of course clear, since I can just consider this minimal polynomial of alpha over K as an element of L of X.